Our first speaker this morning is Greg Turner from HiSeis. So, Greg, over to you.
Good morning, and thanks for coming in for the first talk after the dinner last night. I want to start by just recapping on where things were at the last conference. When Milovan Jurcevic gave a talk on hard rock seismic, at that stage he presented on more than 10 years of research at Curtin University on the use of seismic in hard rock environments. Strategies had been developed to counter issues associated with the very fast rocks in a hard rock environment, so the statics become very important in a hard rock seismic environment. Because we have multiply deformed terrains, we don't have very continuous layers, so need to be strategies for velocity analysis with discontinuous and off-plane reflectors. So in a 2D survey, if the reflecting object isn't directly beneath the line, which is common, of course, in a mineralised terrain, not to have two-dimensional geology. A recognition that in these complex systems, interpretation really needs to start during the processing. You need to understand what your objectives are and have some, the more understanding you can feed into that processing, the better the result that you can get out. And Milovan presented some successful examples of using 2D seismic in mineralised terrains. So step forward 10 years, and HiSeis has commercialised the IP that was developed at Curtin University, and we've now done more than 20 3D seismic surveys in mineralised terrains throughout the world, together with numerous 2D surveys. We've developed over that period a much better understanding of the rock property variations in mineralised environments, and that'll be a focus of today's talk, together with a case history example. We've been regularly imaging steep geology, which I think goes against a lot of people's conventional wisdom that seismic's not useful in steeply dipping geology and looking for steeply dipping features. We've demonstrated the ability to image beneath obstructions on the surface, very important in mine environments, working around open pits, tailings dams, mine infrastructure. But still, it's still early days in the use of seismic in the hard rock minerals environment, and we're learning with every survey that we do. Well, this slide shows the projects that collectively HiSeis and Curtin University have been involved in. Obviously, a strong concentration in Australia, but now spreading right throughout the globe. Surveys have been completed for a whole range of commodities and in a whole range of geological environments. Some of them perhaps a little bit surprising. Our approach to the use of seismic in a new geological terrain is really to use a stepwise approach which minimises expenditure until further confidence can be built up about that seismic can actually achieve the objectives of a project. So we'll normally start with measuring rock properties on core. It can be done very cheaply. Input the properties that we've measured into a geological model and run a forward simulation just to get an understanding of what features may and may not be detectable, or at least a first indication. The next step normally involves the use of 2D seismic surveys and borehole surveys. Difficult to get to image three-dimensional geology with a 2D survey, but we like to go through that step because it gives important information about the geological architecture and also confirms our observations with the rock property measurements that there is reflectivity in the environment, and helps us to optimise optimised survey parameters for a 3D survey so that that can be done as cost effectively as possible. And then finally the 3D survey itself to map the 3D geology, followed by integration with it. We try to bring in every data set we can into a single environment so that a lot of information in seismic data and helping to constrain the interpretation with whatever information you have. So just a very quick 101, what causes seismic reflections? Well, reflections occur at sharp contrasts in acoustic impedance, and acoustic impedance is just simply the product of density and seismic velocity. So the sorts of boundaries that you see in a mineralised environment include lithological boundaries, faults and shears, and alteration zones. Rock property measurements on core is really quite a simple process. We just measure the sonic transit time using that sensor in the middle of the screen there, and wet and dry weights to get density. And using that approach in a core farm, you can usually get 100 to 200 samples measured a day. We compare the data sets generated from those measurements with, again, whatever other geological and other information we can compare them against. So that would include lithology, stratigraphy, assays, alteration logs, other geophysical logs if they exist, RQD, etc., etc. So just an example of one of the logs that we have, actually a downhole log in this example, but simplified lithological log on the right, showing felsic intrusives in a mafic host. And up the top, you can see a very sharp contrast in acoustic impedance associated with that felsic intrusive. But lower down, there's two zones where the zone is considerably broader than the felsic intrusive itself. And we infer that that's due to alteration, which is perhaps a guide for where mineralised fluids might have been flowing. The upshot of that is that you can get enhanced reflectivities from such features where you have that surrounding alteration zones. It's well known that fracturing reduces seismic velocity and therefore can cause an acoustic impedance contrast. But again, alteration around fault zones can increase the reflectivity. So I want to run through a case history from the Darlot gold mine in the Yilgarn in Western Australia. It's an orogenic gold deposit. It's mined close to 3 million ounces. But late last year, it was coming to the end of its reserves, and Goldfields made the decision to commission a 3D seismic survey to fast-track the evaluation of the area around current workings and see if we couldn't find some additional mineralisation which could be accessed in short term around the mine. We did our rock property measurements there and showed that there were some significant contrasts in rock properties, particularly the boundary between dolerite units and the host metasediments, and also between different dolerite units. The 3D seismic survey that was done there covered an area of about 5.5 kilometres by 4.5 kilometres. Extended to at least 3 kilometres in depth, so that's covering approximately 75 cubic kilometres of the Earth, with a cell size of 15 metres by 7.5 metres by 4 metres, meaning a total number of data points there of about 165 million. Approximate cost of that survey, around 2.5 million Australian dollars. The time that it took from first conception and discussion about that survey to delivery of an interpretation-ready product was 6 months. And that included rock property measurements, design, necessary permitting and the lot. We didn't go through a 2D seismic survey in this instance, unusually because of the compressed time frame that Goldfields had to make a decision about the deposit. So I'm going to show a movie to help try and illustrate some of the features of the 3D seismic cube, if you can start the video. The first thing that you'll see is an air photo, and that covers an area which is approximately similar to the area covered by the seismic survey. You can see the Darlot pit there on the left and some tailings, etc. The red lines there illustrate the drilling over the same area, 1,200 kilometres of drilling. The green surface there is 400 metres below the surface, just to give you an idea of how much the drilling was deep drilling and extended below that. Covers only approximately 2 cubic kilometres. That 1,200 kilometres, just for relative sense, if that 1,200 kilometres of drilling was done over 40 years, and if you used a cost of $50 a metre, equates to about $60 million US of drilling. The power of seismic really is the ability to provide a continuous high-resolution image of the geology, and also provide that perspective from the context that you get from seeing a broader volume of the geology. Here you can see a geological map with multiple dolerite units on there, and just here showing that the seismic maps these strong acoustic impedance contrasts, basically raising up a horizontal slice through the data cube with the interpreted dolerite surfaces on there. One of the great things about the seismic datasets is the high sampling density. It allows us in that 3D space to pinpoint intersections between prospective structures and key units. For example, the brittle dolerite unit shown there in yellow, and where it crosses that diagonal line, there's a structure there, and we can pinpoint that from the seismic. Difficult to do precisely with drilling it alone. The next thing that's going to be shown is just how to pick features in the seismic data, basically on multiple depth slices and cross sections, whatever view you want to use. We can build up picks and then put them all together to build up a wireframe. So you do that both on vertical and horizontal sections. So jump to the wireframe there, and it not only shows the position of that structure in this case, but it shows flexures in that structure very precisely. And they're places where you're more likely to have dilation and potential for fluid flows that might be where the mineralisation is. So not only can you see the flexures very well, those bends there, but you can also see variations in the reflectivity along that structure, which, as we saw before in the rock properties, may be indicative of alteration, which may show fluid flow paths. So if you interpret all the surfaces in the 3D seismic data, the structures and the lithological units, other boundaries there, you can build up a 3D framework very quickly, and you can see the timing relationships between the different structures, which can be obviously important for mineralisation. We're just going to slide very quickly through the cube here again, and with some of the structures marked on. Probably difficult to see here, but it's a very large data set, and it's very difficult to show on the screen with one with one view. You look at the data typically multiple views, multiple zoom distances, and with multiple attributes. Okay, so in summary, an understanding of the rock properties is key to the interpretation of these data sets. What we found is that alteration is a key control on seismic rock properties in mineralised environments. Perhaps a bit of a surprise to us certainly when I started at HiSeis, we were using lithological units and just a few measurements in each, but there's a lot of variability within different units. Seismic can be very effective in steep geology and has been very effective in steep geology. And as you've seen today, it's very effective at mapping structures, and you see features of those structures, including the alteration intensity and flexures. So we think it is a new tool for use of mineral exploration, especially as searching deeper. The opportunities for this technology are better deep targeting in areas of known mineral endowment, so you can cover a broad area when you know you're in a prospective environment. Similar scenario, faster screening around initial discovery, so that you can learn more, or fast track learning where the highly prospective zones are around that area. And better conceptual understanding from that, looking at a broader area, volume, or also by doing 2D lines, particularly long 2D lines of the order of 10 kilometres, giving an idea of the major structural orientations, and allows you to see deeper and see what these structures are doing at depth without any real extra cost, so you can see multiple kilometres deep. Also, the capability to map those structures is not only useful for exploration, but very important geotechnically, for mine planning where you want to place infrastructure, and for mine safety. So finally, just like to acknowledge some of the companies that contributed the data that's been shown in today's presentation. Thank you.
We have plenty of time for questions.
To date, we've largely been using VSP, zero offset VSP, to provide, to understand what link the reflectors to the geology and help with their depth conversions. There's an opportunity to use those VSPs from an imaging perspective to further extend those interfaces away from the drill hole. That either requires putting multiple sensors down the hole, and in a minerals environment there's a risk that you'll lose the equipment, although there is new technology coming on stream that might allow us to cover long lengths of the hole in a single pass. And there's also opportunities to put a source down the hole and use multiple receivers on the surface, but that's not an area that we've progressed significantly on the imaging around the hole. Not to say, but the VSPs, the zero offset VSPs, are an important part of the process of understanding the reflectivity in the seismic sections.
At the aisle.
Yes, I just wanted to ask you about your 3D survey. Is it depth migrated or time migrated survey?
We have done depth migration on particular examples. It's challenging. And our standard product would be a time migration.
Time migration.
Yeah. Depth converted time migration. Yeah.
Are you able to
Again, because of the quite broken nature of the reflectors, in a lot of the mineralised environments it's more challenging. We have done some work on that and have seen some features in particular datasets, including the Neves Corvo ore body in Portugal. But and we've collected 3 component datasets as well, and that's part of active research that's going on at Curtin University to better make use of that data. So it's not a standard product at the moment.
Could you repeat the question?
Just asking whether we've used double bounce reflectors in our imaging, and the answer is no.
Just behind you. Go ahead.
Yeah, just wanted to ask you on your acquisition, are you using a single source or are you using multiple sources per shot?
We have used both, but typically we use a single source, whether it be vibrator or explosives or weight drop. Given the steep dips and the need for high resolution, we believe that that's a better approach, and that fold is a better way to build up our signal to noise.
My question was very similar, because you show a HiSeis type of equipment on one of the early slides, and I just was surprised that I thought that was quite low frequency, and you're dealing with a very high frequency environment. How do the two work together?
Yeah, well, a typical sweep is from around 8 hertz to 120 hertz. Most of the environments, particularly with overburden there, don't support a lot higher frequencies, even if you're able to generate them. And the HiSeis is a very efficient source. So, yeah, even if we apply explosives, there's only particular environments where we get higher frequencies.
I was wondering why you consider accelerated weight drops.
Did you hear it?
No.
Accelerated weight drops.
Why we didn't consider them? We have considered them. Sorry, we're just asking why we didn't consider accelerated weight drops, and we've used quite a lot a weight drop without accelerated. We haven't actually. No, sorry, I haven't actually personally been involved with any work with those. I believe Curtin University have looked at that. It's horses for courses, really. You know, we look at the geological environment, what access is available, what the cost will be to mobilise the equipment to site, and yeah, I think everything should be on the table on that front. Yeah. Yes. Yeah.
So, and last question. Oh, Tim.
Thank you. Just in two halves, a technical and then a commercial. Could you just talk a bit more about the steeply dipping reflectors? As you say, it's a challenge to demonstrate the seismic, and how you go about doing that. And the commercial question was, I may have missed it, but the approximate acquisition cost for that, I think it was 75 kilometre cubes.
70. Okay. Yes. So the question was the approximate cost of the 75 cubic kilometres. That survey was of the order of 2.4 million Australian dollars. And the other question was the steeply dipping reflectors, how we go about that, and it's very important to have large offsets to allow you to see those reflectors. And we have imaged successfully features really almost sub-vertically, but certainly 75 degree dipping reflectors as reflectors, and there is presentations I think on our website which show that. But also we see it as breaks in the data, often as what we call white snakes, zones of reduced reflectivity that follow these features, or breaks in the texture, or obviously offsets of reflectors as well. So there's multiple ways that these steeply dipping features
Okay,
can be
I'm
interpreted.
afraid we have to cut at this point and let Greg off the hook and take the rest talk.
Thanks very much, Greg. Okay.